All right, so today we're going to be talking about how the area and perimeter of similar shapes are related. So first I just want to start with a quick review of what similar figures are. So similar figures are ones that have been dilated to be enlarged or reduced. A couple things to specifically remember is that when we dilate a figure and we enlarge it or reduce it, it keeps its same rigid shape. And so all the corresponding angles are still the same. I showed you that in this picture down here. We know these are similar because of the similarity symbol in between the two. And looking at this, every single corresponding angle in this side matches every single one on the larger figure. And then the second one that we're going to use a lot more here has to do with the proportionality. And what it is that every single corresponding length between the two shapes has the same ratio. So in other words, if this side over here between the angle marked 1 and the angle marked 2 corresponds with this side over here, and they're in a 1:3 ratio, 8:24, then that means every single corresponding set of side lengths or corresponding lengths in general has that same 1:3 ratio. So this 12 multiplied by 3 becomes 36. This 7 multiplied by 3 becomes 21. Even a random length that I put in here, just this perpendicular length going to this little V, kind of like an altitude or something. If you multiply that by 3, you get the corresponding length over here of 9. So that we call that ratio the scale factor. I always go left to right when I'm looking at it. So this would be a 1:3 ratio. You could say, though, that the scale factor is 3 depending on which figure you were talking about first, 1:3 or 3:1. Okay, so now let's start actually looking at an example. Okay, so I just made up an example here. Here's a triangle, right? The simplest polygon, fewest number of sides. I put in some side lengths here. So this is a 3, 5, 7 triangle with an altitude or a height of 4 perpendicular to that 3. Okay, so let's just look at the perimeter. So adding those up. First just noticing, so the scale factor of all of these is 1:4. We know it's similar by SSS because there's a 1:4 ratio between each of the 3 sides, going to each of the 3 sides, or just because there's a similarity symbol there. So scale factor 1:4. Okay, so the perimeter of the left one, we add it up, we get 15. Perimeter of the right one, we add it up, we get 60. Okay, area of the left one, just 1/2 base times height. We get an area 6, and on the right, we get an area 96. So let's look at those ratios. This is totally anecdotal. This is just a made-up example. But we get the ratio of the perimeters, 15:6, reduces to 1:4. So that's the same as the scale factor. And now think about it. If I go back up here to how I worded this, this is all corresponding lengths. And the perimeter is just a one-dimensional length. So it is the corresponding length in the left and the right that we're talking about is the perimeter instead of an altitude or a side length. The perimeter still has that same scale factor ratio. So down here, that 15:60 of the two perimeters is the same as the 1:4. Okay, so same as the scale factor. But the areas here, and this is what we're going to really dive into today, is why this is true. The ratio of the areas isn't 1:4. It's actually when you reduce it 1:16 or 1:4 squared. Now, to briefly touch on why, it's because not only does the base get multiplied by 4, but also the height gets multiplied by 4. So if both the base and height get multiplied by 4, when you multiply base times height, now there's a times 4 times another 4 in the base and the height, and we get an area that's 16 times as large because there's a 4 in the base and a 4 in the height that get multiplied together. So the area gets enlarged by the square of the scale factor. If that was a little hard to comprehend, that's okay. We're going to break it down into pieces, but I just wanted to show you an example. Okay, so let's first look at the perimeter. So why is this true? And I'm specifically looking at any general triangle, okay? So if you multiply every single side of a polygon by the same scale factor, we get something like this. Okay, here's any triangle with sides A, B, and C. Okay, those are any numbers that make up a valid triangle. We know from experience like 1, 1, or like, gosh, what's the example? 1, 1, and 10. could not be a triangle because 1 plus 1 couldn't be long enough to reach a length of 10. So just to draw that, so there are some numbers that don't make a valid triangle just because we can't form one, but that's past knowledge. So any numbers that make a valid triangle, a, b, and c here, if we multiply them all by the same scale factor here of m, we get side lengths of am, which could be an enlargement, so larger, or it could be a reduction if it's like multiplied by 1/2. So it doesn't matter whether it got smaller or larger, but we multiply by that scale factor on A, on C, on B. Okay, so the perimeter of two shapes is simply A plus B plus C on the left, and on the right, this AM plus BM plus CM. So just adding up the three sides. Now with a little simple algebra, we could just factor out that M that's in every single side, and we get M times A plus B plus C. Or in other words, the entire perimeter of the first shape has been enlarged by a scale factor of M, just what we noticed up above. Now, one way I think about this is, again, this only works for like whole numbers, but say you multiplied every single side length by 3. So you started with some perimeter. Think of it like jogging around a shape. I started a corner, and my jog is C, then A, then B. Well, if we multiply by 3, what essentially you're saying is go around C, A, and B once, go around twice, go around 3 times, so you count every single side, A, B, and C, 3 times. So yeah, it would make sense that if there's 3 C's, 3 A's, and 3 B's, that we've done 3 laps, so there's 3 times the perimeter. Okay? So yeah, with perimeter, that's clear. Here's how we could break it down into like a simple relationship. So in any two similar shapes, the ratio of their corresponding sides, which we call the scale factor, is actually the same as the ratio of their perimeters, because again, that's just a one-dimensional length. Okay. All right. So the ratio of the perimeters is the same ratio as the scale factor, which is the same ratio as any pair of corresponding sides. Okay. So now let's just think of a really quick example to look at area here. Okay, and this is the sort of example that, say on a test or a quiz, you're totally blanking, you've forgotten the rule. Oh, Mr. Dilloughery said something, it was 1 square, 1 isn't. Well, a really quick example is draw 1 by 1 square and enlarge it by some number. It could be 2, could be 3, could be 5. Okay, so you get a new one. I chose 2. Okay, and then really quickly, you could just, in pink, you could say, well, the perimeter of this shape is 4. The perimeter of this shape is 2 plus 2 plus 2 plus 2 is 8. So this perimeter got multiplied by 2, just like the side length did. So that relationship is the same. So that's one way to just remember a rule, is kind of derive it with a simple example on a quiz. Okay, but notice the area of the first one, which is base times height, is 1 times 1. Now on the right, it's 2 times 2. So actually, we didn't multiply by 2, we multiplied by 2 squared. And the reason is the base got doubled, the height got doubled, so we have 2 times the base and 2 times the height, so 2 times 2, we now have 4 times the base times height because each one has separately been doubled. Okay, now to look at that a little more closely, this is the reason why, okay? With any area you want to derive, we're dealing with 2 dimensions, okay? We're not saying, like, take out your tape measure, how far across is this? Instead, what we're talking about is we're saying, how many square units, like I think of a quilt, like how many square pieces of quilt or fabric do I need to stitch together to cover this desk, to cover this floor? Do I need 277 squares? And you could do partial squares, stitch together and add those up. But how many squares do I need? Well, to find that, you need an X and a Y. This is 2 dimensions. So in general, we're going to multiply 2 perpendicular, or in more dimensions than 2, we'd be talking about orthogonal. But we're going to multiply together 2 things. Anytime you need a 2-dimensional area, you have to multiply 2 things. I mean, think about it. In inches squared has to be made of inches times inches. That's the only way to get square inches. To get a square foot, it has to be foot times foot. To get square centimeters, you have to multiply centimeters times centimeters. So in 2 dimensions, you always have to multiply 2 one-dimensional lengths together. Okay, usually it's a base times a height or some version of that with perpendicular things. In a trapezoid, it's the average of the bases, which is one number, times the height, which is another number, right? So again, it's two things multiplied together to get that two-dimensional area. With the area of a rhombus or a kite, it's a diagonal times a diagonal divided by 2. With a circle, it's pi r squared, so you're multiplying the r times itself. So think about what happens then. If I enlarge every single one-dimensional length by the same scale factor, so every single one of these base, these heights, these inches, these average of the bases, the diagonals, if every single one of those gets enlarged by a scale factor, look what happens. We get base times height becomes base times m times height times m. And so now we get the original base times height that's the same as the original, except now we have this extra m in the first one, this extra m in the second one, giving us an m squared, right? Because you multiplied a enlarged base times an enlarged height, and so now we have two of these scale factor m squareds here. Okay, same thing for pi r squared. If the radius has been enlarged by a scale factor of m, you now have the first radius being multiplied by m, the second radius being multiplied by m. So when you multiply those together, you get pi r squared, the same as the original, times m squared, because each dimension has been multiplied by the scale factor. So now there's two of those m's multiplied together. Okay, so what we end up getting to summarize is that given any two similar shapes, the ratio of their perimeters is the same as the ratio of any one-dimensional length or corresponding lengths between the two figures, and we call that the scale factor. So you could just say the ratio of the perimeters is the same as the scale factor, right? It's the same as the ratio of any pair of sides, any altitudes, any medians, any mid-segments, any two corresponding lengths. Their ratio is the same as the ratio of the perimeter. However, interestingly, when we go from one dimension to two, the ratio of the areas, because each base and height has separately been enlarged and then multiplied together to get that area, the ratio of the areas is actually the ratio of the corresponding sides squared. Or another way to think of it is the ratio of the areas is the same as the scale factor squared. So if you enlarge a single side by a scale factor of 3, the shape gets 9 times as large in terms of two-dimensional area, right? And we could think of so many examples, like, here's a simple example. Here's a 1 by 1 square, area of 1. If we multiply that by a scale factor, linear lengths, by a scale factor of 5, we get 5 by 5, right? So perimeter of this is 4. Perimeter of this is 20. So that did get times 5, just like each individual side. But the area of the first one's 1. The area of the second one, 5 times 5 is 25. So the area got multiplied by 5 squared, right? And so that's how you could see this coming up. So now I'm just going to go through some examples. Stick with me, and then after that, I'll go through, after we do some book examples, I'll switch over to IXL. Okay, so to start off, here's just a table. This is copy and complete the table. So the ratio, and again, it tells us these are similar polygons. So the ratio of some corresponding side lengths is 6 to 11. Now again, you could write 6 to 11 in 3 ways. Either that way with a colon, you could write it as 6 to 11, or you could write it as the fraction 6 over 11. Either way, you're just comparing two values, and that ratio can be really written in any of those 3 ways. Well, the ratio of the perimeter we know is the same because that's a one-dimensional length, right? The ratio of our perimeter is the same as the ratio of their corresponding sides. So down here, the ratio of the perimeters is the same as the corresponding side length, so we get, this is also 6 to 11, okay? But then the ratio of the areas, I'm just going to draw an arrow here, the ratio of the areas is the 6 to 11 squared. And then now this is just like multiplying a fraction, 6 over 11 squared, which would be 6 over 11 times 6 over 11, or the 6 times 6 on top, 11 times 11 on bottom. So we get 36 to 121. Okay. Now down here, it gives us the ratio of the perimeters, but we're going to want to reduce that. So I'm going to use a different color. So dividing each of these by 4, we get that this is really a 5 to 9 ratio. And the ratio of the perimeters is the same as the ratio of any corresponding sides. And you could have called this, you could have said, you know what, this thing, we're just going to call this the scale factor. It's the same thing. The ratio of any corresponding sides and similar figures, that is the scale factor. Okay, so the ratio of the areas then is the square of that scale factor. So we had a 5 to 9 in one dimension, so every single length got enlarged from a value of 5 units to a value of 9 units in that proportion. So if we square it, then the area actually, or the two areas between the figures, actually relate in a 25 to 81 ratio. Okay, so let's go ahead and actually apply this now to find some values here. So this one's saying, well, these are similar figures and we're given corresponding lengths. So these shapes haven't been rotated or flipped over or something. I know this 2 feet and the 6 feet are corresponding lengths. So the ratio of corresponding sides here, aka the scale factor between these, and I'm always going to go left to right here, is 2 to 6, which we could reduce to 1 to 3. Okay, that's the scale factor between these. Now the question is, find the ratios of the perimeters and the areas. So this would be the ratio of the perimeter. Okay, then it says find the ratio of the areas as well. So the ratio of the areas would be 1 to 3 squared, or 1 squared is 1, 3 squared is 9. This would be the ratio of the areas. Okay, again, because we're enlarging each dimension by 3, so the base by 3, the height by 3, so when we multiply 3 by 3, we get an area that's 9 times as large. And it says, finally, find the unknown area. Okay, so we know the original area. I'll do the second half in green here. We know the original area of the red shape was 2. So what I'm going to use is I'm going to use a proportion, because I know the areas are in proportion 1 to 9. So if we have the first area is 2, then we know 2 is to the unknown blue area as 1 is to 9. Because we know the areas have, the ratio of the areas is 1 to 9. And we know the first area is 2, so what do we have to get for the second one? Now, yes, you could have just multiplied by 9 and said, oh, it's 18. But I like to set up the proportion. You go through this, right? You can cross multiply here, so you get, this is a times 1, which is a, equals 2 times 9, which is 18. So the unknown area was 18. Okay, we're going to do that same thing again over here. The reason I'm doing it again is it's not as easy numbers. Now the fraction isn't a whole number. So looking at this, we get, okay, so first we know these are similar. We know these are corresponding. So we get that the scale factor, or the ratio of the sides, is 15 to 20. Okay, if we reduce that by 5, we get the 3 to 4 ratio is the scale factor. Okay, so that right there is the scale factor, which is the same as the ratio of the perimeters. Okay, that was the first thing the problem asked for. Okay, so then to find the ratio of the areas, remember the ratio of the areas is the square of that. So we go, okay, so 3 to 4 squared, or in other words, 9, 3 squared, to 4 squared, 16. That's the ratio of the areas. Okay, and now we're going to use that. And it says find the unknown area. So again, if I know the ratio of the areas between these two, I'm just going to set up a proportion. I'm going to say, well, I know the ratio of the areas is 9 to 16. And I know one of the areas is the larger of the two, is, or the right one, is 240. And the left one, which corresponds with the first thing, which is my 9, has an unknown area. And then I want to go ahead and solve this. So I'm going to just multiply both sides by 240. You could cross multiply. I'm just going to save this step. So we get times 240. So we get that the area equals, now we gotta figure that out. I'll leave that up to you. Let's do it. Okay, so 16 goes into, I think, 15 times. So this and this cancel and give you 15, I believe. Let's see, 10 times 160 would be 160. And then 5 times 16 would be half of that, which would be 80. So yeah, that'd be 168. So yeah, so you get 15 when those cancel. 15 times 9, you get 90 and 45, so that's 135. Okay, I might have made an arithmetic mistake there in my head. All right, so let's do a couple more and we'll switch over to IXL here. So this says that we have these shapes being similar. DE is proportional to XY, so we know that this 4 is proportional to XY, and we're looking for XY. So let's call that XY very clearly. Okay, we know their areas. Okay, so we know that the ratio of the areas is 7 to 28. But we could reduce that to 1 to 4. Okay, but we know that this is equal to the scale factor squared. So if 1/4 is equal to the scale factor squared, then what we're going to do is we're going to say, well, to find the scale factor, I want to take the square root of this. So we get that the scale factor must be square root of 1 is 1, square root of 4 is 2. So that must be the scale factor of the side lengths. Because, I mean, think about it, just to double check and go backwards, let's use orange here. If I were to square this, I would get 1 to 4 being the ratio of the areas, which is exactly what we wanted, right? The ratio of the areas is 1 to 4. So if we want to know the ratio of the corresponding sides or the scale factor, we're going to have to undo that square. We're going to have to inverse it, which is the square root. Okay, so we got the scale factor is 1 to 2. So then we could either just say, well, if it's 1 to 2, we multiply by 2 and get that this is 8. Or, much safer, just set up a proportion and say from left to right, 4 is to xy as 1 is to 2. And then you just cross multiply, you get 1 times xy, which is xy, equals 4 times 2, which is 8. Okay, let's do one more over here. Again, we've got similar shapes to start off with. It's saying find xy, so I know that corresponds to PQ. So looking down here, I know PQ and xy correspond. So I'm going to set up a proportion at the end that's going to say, well, xy is to 10 as, and what we're really looking for is what is our scale factor? What is the ratio of those two sides? Because if I knew it, I could set up my proportion right now and solve. So let's go backwards. Let's say, well, I know the ratio of my areas because I'm given the two areas. The ratio of my areas is 198 to 88. Now I got to reduce that. So first, I just see they're both even. So I divide both by 2, and I get 99 is to 44. Well, now I see there's an 11 in both. So I divide both by 11, and I get 9 to 4. So if I want my ratio of my corresponding sides or my scale factor, to find my scale factor then, which is in my 1 dimension, I'm going to have to square root that. So the scale factor would be the square root of that. Square root of 9 would be 3. Square root of 4 would be 2. So again, you could say, well, if my scale factor is 3 to 2, which is what I was really looking for, because that I can just plug in and solve my proportion now. Let's double check and say, okay, if my scale factor is 3 to 2, then, and again, just to double check, because this is hard to wrap your head around sometimes, then my ratio of my areas would be, just to double check, it would be 3 to 2 squared, or 9 to 4, which is what we have. That was our ratio of areas was 9 to 4, so check, it checks out. Okay, so let's actually go ahead and use this then. What we get is, we get xy is to 10 as 3 is to 2. Just to solve this, all we need to do is get rid of this 10 under the xy. So xy is equal to, and the 2 and the 10 cancel and leave a 5. So 3 times 5 is, xy is 15. Perfect. Okay, so that's all the ones I pulled from the book. Let's switch over to IXL right now. If you feel strong on this, awesome. Go ahead and move on. but I'm going to jump over to IXL. Okay, so here we are on area and perimeter of similar figures. So the figures below, I'm just going to take out my pencil here, the figures below are similar and the labeled sides are corresponding. So we know that the scale factor, the ratio of the corresponding sides, is 4 to 2. I always go left to right. So reducing that, we get 2 to 1. Now it's asking for area. So I'm going to have to find that. I'm going to have to say the ratio of the areas is 2 to 1 squared, or 4 to 1. Okay, so what I'm going to do then is really quickly set up a proportion. I'm going to say 8, which is my first area, is to A2, my second area, as 4 is to 1. Cross multiplying, I get 4A2 equals 8 times 1. Dividing by 4, I get A2 is 2. So my area here is 2. Okay, so I'm not even going to look at the problem just yet. I'm just going to say, okay, the figures are similar. The labeled sides are corresponding. So before I start anything, I'm going to say, okay, well, the scale factor here is 5 to 4. Okay, now what's it asking for? It's asking for a perimeter. That's when I say, okay, I don't need to square it. Sometimes we get so caught up with area, we don't read what it's asking for. So it's asking for the ratio of the perimeters, or it's actually asking for a perimeter. But we're going to use the same ratio, the same scale factor, and say, well, the ratio of my perimeters, P1 to 20, is the same as the ratio of the sides, 5 to 4. Then to solve this, we just multiply by 20 on both sides. The P is now by itself, so P1 equals 4 and 20 cancel, leave a 5. 5 times 5 is 25. Okay, let's just do 1 or 2 more. Here, again, similar corresponding sides. So the scale factor is 2 to 1. It's asking for a perimeter, so we use that same ratio. So we get 12 is to P2 as 2 is to 1, cross multiplying, dividing by 2, we get P2 is 6. Okay, this time it's asking for area. We have 2 similar figures with corresponding sides. So the scale factor is 7 to 5. So the ratio of the areas is 7 to 5 squared, or 49 to 25. Now, we can set up our proportions since you know the ratio of our areas. So we get that the first area, 49, is to the second area as 49 is to 25, so we don't even need to solve this. We know 49 over 25 is equal to 49 over 25. Okay, so we'll stop there because now it's just getting a little repetitive. I hope you enjoyed the video. Good luck.